Recording. Okay, hello and welcome everyone. This is the Ethereum Engineering Group meetup. Today we've got Alexei who's going to talk about Turbo Geth. So Alexei, before you share your slides, do you want to introduce yourself?
Yes, so my name is Alexei. So how to introduce myself? So I basically I'm a programmer profession, and I've been doing it for pretty much my entire career. Started from like 14 years old, and that's why I've always been doing that. So with Ethereum, I've started to be interested in about 2014. Actually, when I saw the paper, the white paper, and I started to get kind of full time involved into these kind of things. About 2017, and this is where I sort of left my previous jobs and kind of went to explore this. And so far, in the end of 2017, that I started this Turbo Geth project, and it's been my main occupation since then. And yeah, so we're gonna in this talk, I'm going to try to cover the topics which I think are the most important ones, but I will try to leave plenty of time for questions, because something which is important to me might not be important for other people. Anyway, and we actually have quite a large team now, relatively, which is kind of surprising to me, because I was never planning to do this, to do it that way. But yeah.
Sounds awesome. So please share your slides.
Okay, so I'm just collected some slides from a couple of previous talks. Let me just share to you. Yeah. But okay, do I? No, that's not the right slide. Did I? Is it? Is this the one? Okay. Okay. So basically, what I'm going to try to talk today is what is Turbo Geth right now, because it does change quite a lot over time. As it started as the project to try to profile Go Ethereum, and then it sort of migrated into something else. And now I see sometimes we get, at some point in the future, we come to the point where it will become less about performance, but more about processes, about how you develop things. So I'm not going to go through the history. You probably can look it up in my other talks. I'm just going to try to go over the main crucial differences that Turbo Geth has between the Turbo Geth and other implementations, specifically Go Ethereum, that it's been created from. And now I wanted to say that now the Turbo Geth is substantially different from Go Ethereum, and we're actually probably going to rename it and some very soon, because the name would not serve the purpose anymore, because a lot of people get confused by assuming that the Turbo Geth works in a very similar way. In some cases, yes, but it will be not the case in maybe, let's say, in a few months. It will be completely, most of the pieces of code will be replaced. So the main idea behind Turbo Geth is essentially start storing the data in what people now call the flat format. And it came from the observation that in the majority of the Ethereum clients, the Ethereum state, which is the kind of the main thing that the execution of transaction needs, is stored in the form of some kind of serialized tree. And so the way it is serialized usually is that on the left-hand side, for example, we see this kind of tree, which in real life it's got a it's got degree of 16, which means that every node can have up to 16 children. But in this picture, in order to make it a bit more accessible, I did it with degree 4. But this picture basically illustrates there are different types of nodes in this tree. There are branch nodes, these ones. There are what they call extension nodes, which basically are something in between two branch nodes if you look at the path. And there are leaf nodes, which are these diamond-shaped things. So they were introduced, these three different types of nodes were introduced when Ethereum was designed to make the tree representation more compact. So because theoretically you could represent the entire tree only with without those extension nodes, but only with the branch nodes. And so you would have, let's say 16, oh no, sorry, not 16. You would basically have a branch node all the way through. But of course, you would realize that in such scheme, there would be a lot of branch nodes which have exactly only one child. And this was considered wasteful, and therefore the things like the extension nodes and these things were introduced. Nevertheless, so on the right, you can see how this is currently in most implementations, how this logical structure on the left is actually physically stored in the key value store. And what is used here is the sort of the hashing is used as the as kind of the fingerprint or digest of the node. So each node gets converted to a string of bytes using this RLP encoding. RLP stands for recursive length prefix, and then which could be variable size depending if the node is large, like the branch nodes are large, and the RLP could be I don't know, 500 something bytes, whereas the leaf nodes could be quite small. I don't know, maybe 60. Like for accounts, I think it's about 80 bytes. So it's quite a big variation. So applying the hash function to it makes it fixed size, but that's not the only reason why it's done. And the value is actually this RLP encoding, which you could use to reconstruct the node. So using this, if you look at these two pictures again, if you see all these arrows on the left-hand side, you can think of them as the pointers. If you think about, let's say, this structure existing in the memory of your process, and then there are pointers between these different parts of the structure. So you can find the correspondence between these pointers and the records in a database. So each arrow is essentially a record in a database. And as we usually talk about dereferencing pointers or like walking through the structure in the same way, that maps into looking up and this thing into database. So when you logically try to walk through the structure, let's say that we want to walk from the root of the structure to this V5 diamond. So in the logical structure, we would need to do how many dereferencing? 1, 2, 3, 4. So 4 dereferencing of the pointers. In the same way, it will translate 4 lookups into the database, because we first look up the root. I believe, where's the root? Here, yeah, the root is on the bottom. And then once we get the root, we need to get this fourth. So we know this fourth element, which represents the pointer to another one. So we do look up to this penultimate element and so forth. So we do 5 lookups, and then that is how we get to the value V5. And observe that those accesses cannot be parallelized, because the next access requires the information which we got in the previous one. So this is the main starting point for Geth, this observation that to access element in the state, you have to go through these sort of virtual pointers and access database quite a lot. And that was apparently a bottleneck back then. And so just jump a little bit forward. This is basically what Geth replaces it with. It replaces this state with the structure, which is basically optimized for EVM access. So what EVM does not look at the any kind of tree structure. It looks at the state as a mapping between addresses of accounts and the values of accounts, and also storage locations and the storage values. So the EVM, in its current version, does not know about Merkle tree. Doesn't know about any kind of this rules about the extension nodes or branch nodes or anything. So why do we actually have those things? Why do we store it? Well, this slide should explain why. So it's schematically shows what happens during the block processing. This could be either processing of the historical blocks when you try to catch up with the chain, or it could be online when the blocks just come in and need to be processed. So schematically here is that you have in each block you would have a header which has some fields in it, and then followed by this there's the block which has multiple transactions. And so this little star here is it's supposed to be this cog thing that executes, just kind of executes transaction. In order to execute transaction, one of the inputs you require is the current state. And so basically the reason why it says here historical states is because at the time when this execute, this was actually the current state. And once we passed that block, it became historical. So each execution produces the final, so the next state, and it also could produce some things like receipts and logs. So the reason why I show you this picture is that the state root hash is one of the fields inside the header. And what we're supposed to do when we are executing the blocks, we are supposed to somehow calculate the state root hash of this state that we produced after the block execution, and we're supposed to compare it with this yellow thing, which is the state root hash. And that's the entire purpose of having having all these things, right? All the calculation of the root hash. It's not required by EVM, I repeat, it's just for the process of like extra verification. And you also can notice that it's not strictly required that you have to do this for every block. And that's another interesting observation that I made, that a lot of people think that, you have to compute the state root and compare it at every single block. Well, no, that's not true, because you can actually skip, if you don't want to, you can skip to the, let's say, latest block that you have and only compute it there. I mean, this is the assumption that, for example, a fast sync makes, that it doesn't actually compute the state root hash for the entire history. It just computes it for this kind of snapshot. And you can relax this rule. You can play with this idea a bit more, where you say, like, if I'm happy with my Ethereum client to give me a slightly lagged representation of state, let's say 16 blocks back, then I might just compute the state root every 16 blocks or something. So it depends. So if you know really exactly why this is happening and not just blindly doing it, so you can actually find some interesting optimizations. So, but the problem here is that so there was a sort of a trade-off, apparent trade-off that people made. They say, okay, because we have to do this kind of stuff, right? Because we have to calculate the statehood hash root, there's no other way. We have to store the state in this particular way. We cannot store it as a flat way because we won't be able to calculate the state root. I mean, we understand that, yeah, EVM doesn't really like this format, but what can we do? It has to be a trade-off. But I think the trade-off was a bit false. So we could actually find the efficient way of calculating the state root without having to store the data in this particular structure. So what happened here is that this is I'm going to exemplify use of the solution. So why is it challenging to calculate the state root from the flat data, and how this challenge could be addressed? So in this picture, imagine that the state is a collection of some sort of leaves, and this is the logical tree that in this picture it's binary. In a real life at the moment it's got a degree 16, but anyway, this is for just illustration. So one way we could go about it, which is very naive, is that to take the entire state and walk through it, iterate through it, and then build up the state root. I mean, we don't even need to build up the entire tree in memory, as you might realize, but we can have a stack which will basically accumulate, have a stack with one item per tree level, at which we accumulate the current running kind of hash, and you could imagine how it could work. So you have a stack, and then it basically just moves through the tree, and then in the end, the top of the stack would accumulate the state root. But even that, so that basically means that we don't have to blow up the memory. But although we don't blow up the memory, we still have to walk through the entire state, which could be quite a lot. I mean, I think it's hundreds of millions of records, and even on a very fast disk, it might take you half an hour. So that's half an hour might still work if you want to be really delayed. I mean, one naive implementation would be to, okay, we are going to be always delayed for I don't know, half an hour. It's how many blocks? I don't remember, but let's say 1,000 blocks or something. So we're going to calculate the state root every 1,000 blocks and so forth. So that's kind of already working, but not for pretty much any practical use cases. So what if we calculated the state root somehow, and now we have to modify it? Let's say we processed a new block, and then we need to find what is the new state root. This is actually the most common problem. And and also imagine that you actually utilize your computer memory, and you manage to save some of this tree just in case, not in a database but in the memory, to make sure that it's basically some sort of caching, so that you might be able to calculate the root faster. But the problem is that, let's say that we modify the element which is outside of our cache, is kind of unreachable. And so what we used to do before is this: we will identify the sort of the region of the state, which could be quite large, which is basically where our modified element is. We rebuild the entire subtree so that we can verify, okay, so we map it to the element that we have in memory, and then therefore we can compute the new state. Because basically the reason why we need this whole subtree is because we know, since one of these elements changed, the entire the root hash of the entire subtree is going to change, and we need to know what it is going to be. So that's why we need all this. So we load it up, we compute using our nice algorithm, we compute a new state root, we update it, and then we propagate this all the way to the top. But then we basically, because we don't want to accumulate the entire tree in memory in the end, we discard. We just have to discard something so that we can keep our cache warm and relevant. So we discard those things. So maybe, but that means that the next time if we need something here, we have to load it again. And so that was how TurboGeth used to work at some point, and it kept loading and loading lots of data. So that was kind of the bottleneck. So what is the solution to this is actually, we just started to store those intermediate hashes, the ones that we would normally compute. Here in this picture, we actually compute them every time, but instead of computing them every time, let's store them. So we store them in the database, and the way we store them is we take the prefix, which is the kind of the path from the root to those elements, and the value is the hash. So I actually claimed in my previous presentations that the size of such structure for the entire state was about 2.5 gigabytes, but this was found to be untrue. And because we basically found that the database we were using were inaccurately reporting the size, and I think the updated figure is about 7 gigabytes. So it wasn't as good as I thought it was, but it's still not too bad. So having those additional 7 gigabytes of those kind of cyan records, we actually can help ourselves. If you can sort of imagine how we would use this, because we were treat them as already pre-computed trees, so we don't need to load these things again. So all we do is just simply use those things to recompute only the parts of the Merkle tree that we need. So that's our solution to this problem. And this is how we reconcile this sort of apparent trade-off, which we think is not really a trade-off. And that's basically at the core of the first innovation in the TurboGeth. Yeah, so essentially in this case, we just load this, and we, instead of loading the entire subtree, we just load this these entries. So quickly go to the next innovation, I don't know. I mean, doesn't look like a much like an innovation if you look at this picture. So the idea is
Okay.
that,
Yeah. Could I fire a question in?
yeah, sure, yeah.
So yeah,
Okay.
so for the previous slide there, so your hashes are 7 gig, and I guess the leaves have to be stored, so they're a certain amount. Are you saving any disk space at all, or is it just improved performance that you're getting?
Yes, we do save the disk space. I think again for the leaves, we also realized that our previous measurements were incorrect. So we were saying that the leaves were about 10 gigabytes. It turned out that they were actually 38 gigabytes. So that 38 plus 7, yes, 45. We are saving some space. I think the difference here is that our keys are probably much smaller. That's a very good question. I think we're saving a bit of space, yeah, but not extraordinary amount of space in this particular for the state representation. I think where we save most of the space is for history. So when people talk about archive nodes taking 5 terabytes and archive nodes taking 200 gigabytes, the difference there is not mostly how the state is represented, but how history of state is represented. Because if you actually represent the history of state as Merkle trees, it does turn out to be quite large. But if you do it in a flat sort of diffs way, then it's much smaller. But yeah, to answer your question is that, yeah, the biggest win here is from the access, access performance rather than on compactness. We thought we had a really good compactness, but that turned out to be not so true. I think it's still pretty compact, but not as compact as we thought.
Okay, that makes sense, and thank you.
Mm-hmm. Thank you for the question. That was a really good question. So stage sync. So this is something which kind of came a bit more recently. I think it was this year. Is that so? Usually, in this picture, you would imagine how the Ethereum client would work when the blocks are coming in 1, 2, 3, 4, and each block you can imagine that it's like a pipeline. It needs to process first process headers, check for the certain hashes, and then it needs to do some other work like recovery of the senders, and then it needs to execute the actual transactions, and they need to compute a new root hash and so forth. So there are many stages, and then build some indices. And imagine in this picture, there's 7 different stages. And what the most implementations are trying to do, they try to utilize the concurrence, utilize the fact that you have multi-core CPUs and stuff like that, and just start doing things as much in parallel as possible. So you get asynchronous kind of execution. So in this diagram, you can see the processing of block 2 starts straight after the first stage of the block 1, and so forth, and then you get some sort of win. And so it is counterintuitive. Why should you do it in a way on the bottom? Because that's basically like, okay, let's first ingest all the blocks that we could. Usually that works pretty well for historical blocks. We ingest all the things, that 11 million or whatever you've got. And instead of trying to run them in parallel, we first process all of them for the first stage, and then through the second stage, and so forth. And initially, I remember discussing this idea with people in March when we were in ECC, and I said, you know what, I think there is something in it. We did some first experiments, and I thought it sounds like it should work actually slower. But I had some weird intuition that it's going to be faster. And it was faster. And the reason why it was faster, mostly it's to do with the way the databases work, but also it's something to do with the way the people work. So which one is going to be the first? Okay, so let's start with the databases. So the way the databases work, at least the one we're using is called the B-tree database. It's LMDB, but other databases essentially if you look at the key value, pretty much all the key value store databases, they are sorting the content by the keys. And this is how they can retrieve things quicker, because everything is in a sorted order. But so what people do mostly, if they insert some kind of random looking data into the database, what happens is that the database essentially sorts it. So you throw things in a random order, and database kind of does a lot of work to sort it, and then you can use the sorting to access elements. But what if you're so you're essentially using the database as sorting algorithm plus some kind of access. But what if you actually did not want the database to sort the data, but actually you sorted yourself first using other algorithm, you like fast sort, quick sort, merge sort, whatever you know, or combination of this, you can make it really optimal, and then insert it already in pre-sorted order. Would it work quicker? And yes, it would. So especially if your database has some way of being told that, okay, look, I'm inserting the data is already pre-sorted order, don't do any sorting. And for example, LMDB allows this. There's basically the difference between insert or upsert, people call it upsert, and append. So when you do append, you tell the database, trust me, the data is in sorted order, trust me, you don't have to do any other comparisons or any sorting, just, you know, fill it up, fill the buckets up. But even before that, even if you don't use this feature, it's still quite much quicker, because you end up basically filling the space continuously and sequentially. And it turned out to be quite a large improvement for most of the things, because essentially, if you look back into this slide, so one way of thinking about what does the Ethereum client actually do, so they, for each block, they ingest, let's say, a header and a block body, and that's it. So that's after that, they can do this stuff without doing any interaction with the network. So they've just received this primary information. Let's say it's the first two stages, it's a red and an orange, and everything else, this yellow, green, whatever, blue, this is all basically the data transformation. We take some input data, we do something with it and put it back into the database. So all these things are just transformation of the data. And a lot of them is, so some of these transformations are kind of changing the order of the data. For example, one of these transformations that take the data, apply the Ketchak to the keys and put it back. That's one of the transformations. And obviously the Ketchak application messes up the order, right? So what you have to do, if you want to kind of use your method of pre-sorting the data, what we do is basically load it up. We hash it, and we, instead of putting it straight in the database, we put it in the files, and then the files are pre-sorted. Then we have a bunch of files, and then we do merge sorts from the files back into the database. But when it touch the database, it's already pre-sorted. So basically, we look at this, most of the processing is essentially just simply data transformation. And we can optimize it if we know that they happen on large scales, like 100 gigabytes read, some sort of sorting, shuffling, caching, whatever, and then load it back in. Or some sort of indexing or something like this. So indexing could also be quite a lot of, optimized quite a lot if you do it on a large scale, as you can imagine. So the more you basically, the more you chew, the faster you, sorry, the more you bite, the faster you chew, I would say. And so that also explains this sort of this non-linearity and the shape. So on this chart is very weird, but so what I was trying to show here is that on the x-axis you say how big is my chunk, how many blocks I wanted to process in one single go, and on the x-axis, on the y-axis is how quickly can I do it per block. I mean, so what this sort of chart illustrates is that the more you bite, the quicker you chew. It means, like, if you take 1 million blocks, you will process it quicker in terms of time per block than if you take one. And So this non-linearity explains why we could sync a bit faster. But the second reason, I mean, also this is a quite interesting corollary to this, is that we tried it on a hard drives, and on a hard drive you cannot currently, with our current algorithms, process one single block faster than, let's say, 13 seconds. It takes you longer. And you would think this is actually a verdict that you can't sync with HDD, but with a non-linear processing time, you actually can. That you wouldn't be processing block by block. You would processing, let's say, every 16 blocks. But still, so you can still have like a view of the Ethereum state delayed by 16 blocks, as I was telling you earlier. So you're essentially computing a root hash every 16th block, and if it's okay for your purposes, that's fine. And then the other thing to do is with the people, I said, right? So one thing about one reason why this is faster is databases. Another reason why the people, because if you look at this picture or look at the bottom, and imagine that you're doing a profiling of your program, your profiler on the top would basically just give you the picture that everything happens at the same time and there's lots of stuff happening, and that's actually harder to see what is the real bottleneck. If you're actually profiling the things on the bottom, you can profile just a single specific stage, and there's much less stuff going on, and you can see things more clearly. And this is actually one of the reasons why we started to see things more clearly and optimize. And I think that's also quite a good reason, quite a big reason for that. It's not magic, but it's just simply how people's minds work. So you're kind of divide and conquer kind of thing. So yeah, let's see. And the remaining part of my presentation is going to be about another thing which happened even more recently. As I said, the TurboGeth is just evolving. Like what is at the core of it is evolving. Started with performance, then we get we're starting to get with the stage sync. We get into the kind of human component of it. Like as I said, that it might become in the future more about the process than about the technology. And this is where the third part will be even more about the people and the process than about technology. So here we talk about diversity of implementations and consensus failures. So when you hear, if you listen to any kind of core dev calls, you might hear the phrase consensus failure quite a lot. What it means is that if you have two implementations, and they behave differently in a situation where they should behave the same, like processing certain instructions or in certain situations, they create two different behaviors, and they essentially diverge. And usually that means that either chain splits or one of the implementation basically gets stuck or something like that. So with my observations were that most of the consensus failures happen not in EVM and not in other places, but in a specific place of the implementation, which I call interblock state. This is the place where, let's say, hashing within the block, caching within the block happens, a self-destruct, refunds, and all this stuff. I mean, if you remember, there were a few errors in there, and usually they happen in this place. And the reason I'm talking about this is that, so the third thing about TurboGeth now is that we're splitting out, we're basically breaking up the monolithic piece, which is the Ethereum client, into many components. But we're not just doing it for the sake of splitting it. We're only splitting the things that we think make sense to split, which means that if it's either useful to have multiple implementations of these things, or it is useful to have multiple instances of these things, we're going to split. So in this case, we have split. The first kind of split was that, okay, let's try to re-implement that thing where the consensus engine failures happen. And also this is where we identified our next bottleneck. Let's implement in C++. And this is how the project Silkworm started, because we first just tried to integrate EVM1 engine, which was written by Pavel Velitsa and his colleagues. We just tried to integrate it into Go Ethereum, and it worked, but not very great because there was the overhead of communication between Go and C code. So we decided to wrap it around in some C++ code, and currently it works, and actually it works pretty well. And the reason why I show in this slide, we're currently working on a version of TurboGeth where it throws away this EVM and the layer around it, written in Go, and replace it with Silkworm. And for the purposes of like a consensus failure, this is already pretty much a different implementation already. And that that means that TurboGeth will be able, at least for some time, to run in these two different modes, which you can regard for consensus failure purposes are different implementations. And that's, you know, kind of when we start arguing about client diversity, that's not step backwards, it's actually step forward. So the next thing is that we already for the RPC daemon split. So this is one of the examples where we decided to split the node into two pieces, and so we split out the RPC daemon, which is currently this is currently how you run TurboGeth. If you want JSON RPC, you have to run a separate component to provide you with this API. And it started again. It started as the performance optimizations because we realized that a lot of people would run many RPC daemons against one TurboGeth node, and TurboGeth basically just provides the data, and RPC daemon uses its CPU to do all the JSON things and maybe execution, because it's quite CPU intensive to run RPC daemon, and you don't want to run out of CPU and then have to install another node, because node can handle more data than it has a CPU available. But now it's actually also splitting up into people who already started using RPC daemon, and some of them find it more flexible design, that you can have multiple, you can put on a different machine, you can like put it on many machines. And also in the future, what I would like to do is that I would like us not to maintain RPC daemons anymore. I would like this to be a complete spin-off. If we stabilize the interface, by interface I mean the communication between RPC daemon and TurboGeth, or it could be other implementations if they adopt this interface. So I just want to say, okay, now there should be another group which will work on RPC daemon, and they can do their standardization and things like this. And this is actually, from my point of view, one of the reasons why people wanted to do our JSON RPC standardization, but it never quite happened, is because the working group that would work on the standardization would not be able to actually enact their standards, because they would have to go back into the client implementers and ask them to, okay, can you please do this change and that change. In my vision of the future, that working group will simply do their own work, and they will basically ship the RPC components, and they will be compatible with pretty much any implementation. So they will be able to enact their own standards and stuff like this. And this is going to be pretty much completely separated from the Ethereum core developers, who don't really, I mean, at the moment, I don't feel they have a much appetite to work on the RPC standardization. And that's okay. Just that if you don't want to work on this, I think you should give the other people ability to do that in a good way, so they don't have to kind of come and ask your permission all the time. So, and this is basically like, just to exemplify, we use protobuf and gRPC for the interface, and this is the example of how currently the interface looks like, but it will be extended pretty soon to support some other things. And I'm gonna just quickly show you, I think I'm just took more time than I thought I would. The other sort of splits we are working on for different reasons. So consensus engine split, I guess that's probably, it's quite a difficult one, but I think it's going to be pretty awesome when we split it up. And this is like the conceptual kind of the interface, how the interface could look like. And again, you know, we could, if anybody is interested, we could talk about this. So another example is, which also is kind of worked on, is peer-to-peer sentry split. And the idea here is that you remove these specifics of peer management and the discovery from the node, and you make it the responsibility of the separate component, which again, and you can have a situation where you have a multitude of those components per node, or the other way around, you can have one sentry serving multiple nodes. I mean, the possibilities are, which you start thinking about these things, is like, well, this is completely makes sense, and this opens up quite a lot of flexibility for people installing this thing. Like, for example, you can think about rolling restarts, right? If you have two sentries connected to two nodes and you need to upgrade them without any interruptions of service, I mean, of course you can like upgrade them one by one, but without even losing any peers, because you can like, you could imagine how this would work. So this is again the conceptual interface which we're currently developing and using, and then another thing we're working on is the splitting up transaction pool, which is also quite important. You probably heard about the talks about MEV, EIP 1559. So I think this work would benefit, or account abstraction, this sort of splitting transaction pool up would benefit those areas quite a lot, I think. Because again, this is about sort of delegation of this work to other people, rather than, because I know that the Ethereum core developers are quite busy and they very rarely make changes in transaction pool logic. I mean, it's a very complex piece of machinery, and they need to get distracted. So the problem has to be serious enough so that they can go and work on it. That's why the transaction pool doesn't really get a lot of attention in terms of people experimenting and implementing things, because they know, oh, it's going to be pretty much impossible to put any sort of exciting new changes in. But I think the future which we're trying to build here would enable that. So you would enable people creating different implementations of transaction pools, making them interoperable, creating different networks. That's another interesting thing. With the sentry and with the transaction pool, you should be able to create new networks and experiment with them. So yeah, that's basically that's why I'm thinking that the third part of TurboGeth sort of project is about creating kind of a much stronger ecosystem where you would have multiple working groups working on things, but the working groups which will be empowered to produce their own products and not having to always go back to the core developers and say, okay, can you please implement it, or can you please review this? So they need to be able to have their own code to ship, and this code will be used by people in the ecosystem. I think it's all for me. Yeah, I'm going to stop here, and we'll see if we have any time for questions or anything like that.
So in your updated, architecture that, has been evolving, what performance do you think you're getting relative, say, to Geth at the moment?
I mean, performance is very multifaceted thing. Which part of the performance?
Well, a good one is how much gas per second,
Okay.
could you do?
So we actually do have a we can do much more, the gas per second than Geth, and maybe 10 times more. But the what we need to be careful about is the worst cases. I mean, there are average cases. In an average, we do much more, I think at least 10x. But in the worst cases, we might not do more than, we might not do 10x. So we're actually looking at the worst cases, and people call them DOS attacks or something like this. So there are different tricks that people can use to, to slow down the processing. And we currently look at the different types of these attacks. So the ones which are related to state access, which is where TurboGeth actually shines quite a lot. But there is attacks which are based on simply computations like precompiles and cryptographic opcodes like SHA-3. So with those, I think they are quite likely to become bottlenecks if we start raising the gas limit. And one of the, currently the way to protect against this was that, okay, we're going to just keep raising the gas cost of those things, which are becoming the bottlenecks. Obviously, that sort of works, but it's very it's a very difficult process. So actually, one of my hopes is that when we separate the transaction pool into a separate component, I'm hoping to create another layer of defense in Ethereum network, defensive layer, in which if you can afford to run multiple transaction pool instances around your node, and you can set it up so that instead of simply looking at the balance of the contract, they could also try to execute this transaction. Maybe they do some sort of load balancing and try to execute them. And if they can basically restrict those transactions which are using the computational opcodes to try to make execution slow. And let's say that they won't propagate transactions which are slower than 1 second or something. And so this extra layer of defense would allow you to do those gas repricing maybe less frequently and more predictable schedule. And then it will also allow you to a bit more open about those vulnerabilities, because at the moment, if somebody discovers this new kind of gas related vulnerability, it cannot be openly discussed, right? Because somebody can exploit it. But because we don't have any other layer of defense, if we had those extra layer of defense, that means we knew that, okay, we can rely on this layer while we talk about this vulnerability, and we're going to fix it on the layer 2, like not layer 2, but on the gas level. So we can still run the predictable schedule of these adjustments, but we not solely rely on this stuff.
Sure. I guess that wouldn't help you though if the transaction was already in a block that another client has created. But yeah,
this is a very common question. So there are two types of there are two threats that we want to defend against. So threat number 1, when transaction is already in a block, and threat number 2, when transaction is in transaction pool. And so you can deal with those different ways. So when transaction is already in a block, okay, so you don't you just have to execute it, right? People have to execute it, or they have to orphan that block. I mean, depending what happens. So if people basically refuse to execute long blocks, then they can just orphan. Majority of network can do that, or you can just basically just get over it, just execute it, and then you'll slow down for a little bit. But the second threat is when the transactions, these big transactions coming from a transaction pool, it's a different thing. So you can defend against it using this sort of like extra layer, because what you want to avoid it to go into the block in the first place. But if the miner wants it to go into the block, it will go into the block. The other question is that, does this miner want this to be orphaned or not? Because the miner, if the miner wants to put a big transaction in a block, they need to have a plan. Whether they risking that everybody will reject that block and will say, okay, too slow, we're not going to build on top of that. Or if nobody, basically, if you're watching for those things, that the miner is probably not going to do it either, because they don't want their block to be orphaned. So, yeah.
Thanks. That makes sense.
But I think I would say that architecture is, back into your question, this kind of, if you talking about the splitting things up, the way we are trying to split things up is without pretty much any effect on the performance. I mean, there might be some effect, like in the, let's say, in the peer-to-peer sentry, for example. If you have things inside one process, you might be able to get the data quicker. So we are alleviated by let's say if you're running on the same machine, you can run in a shared memory mode. But very recently, we actually had this idea about if you, let's say, want to rewrite all the components in the same language. Let's say we started writing the peer-to-peer sentry in Rust. I mean, we have a Go implementation and we have a Rust implementation. Okay, why is it useful? Well, then we are going to write the transaction pool implementation in Go and Rust. Eventually, if you have a, let's say, peer-to-peer sentry and transaction pool in Rust, then it allows us to have two options. We can either build them as two separate processes, or we can build them as one single binary. And then it sort of gave me the idea that, you know, if somebody produced the implementations of all these pieces in the same language, then they can again keep building it as the same binary without having those gRPC links everywhere. So if you really want the simplicity, and if you want to run it on a dApp node as one binary, that's basically the option for you. If you're running it with in your network, and then you want really flexible opportunity, little flexible options, like I'm going to run 5 RPC sentries, sorry, 5 P2P sentries, I'm going to do 6 RPC daemons, then you're splitting it up and you're putting it in different places, and you're kind of orchestrating this thing. So that's kind of gave me the idea that, gave us the idea that there would be an incentive to actually having those components implemented in different languages, rather than essentially having one rubber stamped version of everything.
Paul has put a question in the chat. Can you see the chat?
Okay, let me try. Should I unshare the screen or not yet?
I think you could unshare the screen. I think, yeah, you don't need it shared.
Okay, stop share it, because I might be able to see the chat better.
Yeah.
I currently...
Oh, look, I'll read it out. How relevant do you see this architecture as we move to ETH2? How has it influenced validator implementation?
I don't think it has influenced validator implementation, to be honest. As far as I know, I haven't been watching the validator implementations much, but I think that the idea of sentry is already been discussed in the ETH2 implementations. I think this idea is not very new. I mean, I think it has been written about and discussed even in the context of, if you think about libp2p, they have a daemon, they have this kind of, you can think about libp2p daemon as the sentry, essentially. So it's not a new thing. I don't know exact details, but I think this architecture will be quite interesting for any such large system. I mean, I think basically Ethereum 1, at least, it has come to the point where if you want to keep growing, you have to split things up. You know, otherwise you can't keep growing. You can't have this one huge thing, you know, and it needs to be worked on by many more people than it is worked on now. So you have to start pulling things apart. You mentioned performance comparison to Geth. Have you compared other clients like Bizu? So it's very difficult to do performance comparisons with things, and I don't really find it very kind of top priority to do comparisons, because I know that there are certain things that we do much better. I don't want to spend a lot of time trying to do correct comparisons, because I don't think it's a good investment of our time at the moment. And in any case, that I would prefer other people to do that anyway, the third parties, to because people will trust performance numbers produced by the third parties more than our own numbers, because, you know, we could try to boast with like, oh yeah, we just I would rather these numbers will come from the outside. I have a question on high availability. Have you explored options for sharding, replicating the state across multiple nodes? Generally, running a pool of nodes can raise the problem of maintaining single source of truth, whereas sharding deprecated to be. Yes, very recently, I've been experimenting with the sharding of the state. Yes, and there are two general approaches that kind of been tried. It's not like on the main roadmap, but first try to simply split up the state into pieces and run them on multiple machines, and then do some kind of communication. So one thing I tried is that basically all the shards, they do the same exact processing, but they have their own pieces of state. And whenever they hit the state axis where they need to read something from the state, only one of them has the state and everybody else doesn't. So what happens in this point is that the machine that does have that piece of state, it broadcasts the read results to everybody else so they can proceed. And so essentially this is kind of the barrier synchronization. They all hit the barrier and one of them broadcasts the result, and then they keep going. And of course the problem here is latency, and I didn't go with this experiment very far. There are other experiments would be done that where you have one processor node and multiple data bucket nodes, which basically store different pieces of state, and they somehow, you know, communicate and using some kind of persistent cache or something like this. I mean, these things are being explored slowly, and generally to this question, I think that this is the approach to sharding I would rather take. You know, it's my personal kind of conviction that you have to, these are quite complex concepts, you have to explore them gradually, you know, using some working implementations, and then just, I think we might come to sharding from the different kind of direction in the end.
I have a very quick
question.
Okay. What are you observing as the main bottleneck after all those optimizations applied? What is the bottleneck at the moment?
I think there are two bottlenecks. There's still the state axis is still bottleneck, and that's why not for the reading like a non-existent state, because we can actually squash it with the Bloom filters or something. But if you need so the kind of some of the worst case blocks that we're producing are the ones where you're basically forced the EVM to read lots of accounts or something. So that basically becomes quite slow. But as I said, that this is followed closely by the computational bottlenecks. Look, by computational bottlenecks, I mean precompiles and cryptographic things, because I think they are going to be the thing that, so even if we solve the state problems, they will be the things that will not allow us to raise the block gas limit substantially. They will become a bottleneck.
Okay, and so the EVM is pretty far from being the bottleneck, right? I mean, the EVM
no,
execution.
It's not actually super far. It's not that far. It is kind of closer when they thought. So basically, back in May this year, when we started Silkworm C++ project, this is the point where in our profiling we got to the point where the state access wasn't the main bottleneck anymore. It was kind of split between three equal parts. There were state access, garbage collection in Go, and the actual CPU usage. And we decided, okay, if we want to slash the garbage collection part, we tried as much as we could to remove the garbage, but there's only so much you can do in languages like Go before you get into a completely unreadable code. So we decided to have an experiment to do it in C++, and it did get quite a good result. So if you compare now the biggest sort of the longest stage, which is processing all the blocks, all historical blocks on Geth with the same machine. It takes about, let's say, 32 hours. On Silkworm, it takes about 18 hours. So the difference is most probably is a combination of CPU and garbage collection, because they do exactly the same state accesses and do exactly the same they use basically the same database. They do it in pretty much the same way. So I would say this 32 minus 18, I mean, how much percent is that? So I think it's kind of consistent with what we saw before, where the bottlenecks. So we using the C++ implementations, we were managed to reduce the garbage collection and CPU overhead, but I think we're still stuck with the IO overhead. I think Andre, who wrote this Silkworm implementation, so he said that now IO is definitely a bottleneck, because we kind of removed we squeezed out most of the other things out of it. Cool. Right.
Are there any other questions? Okay, look, I'll quickly find the last slide and I'm going to share that. So just give me a few seconds, share. Yep,
it's not a question directly on the talk, but any comment or thoughts on PayPal's announcement that they're going to support for the major cryptocurrencies?
Is it the question to me?
Yeah, just any thoughts? I don't know.
Well, I do not. I used to, I mean, maybe a couple of years ago or 3 years ago, I used to follow these things and I used to try to form opinions about this, but I found myself unable to do so for the last couple of years. So unfortunately, I wouldn't. I don't know, because I simply didn't have a mental capacity to actually think about these things.
Yeah, I think they've had rumors about wanting to do it for many years, but it looks like they've finally actually done it. So that's I think it's very interesting.
But it seems like you can, at the moment, PayPal is only talking about accepting cryptocurrency, but not paying with it. So I think you're still going to use your credit card to pay dollars. So it's going to be people buying stuff using their ether. So they're going to, it's all, yeah, I'm not exactly sure. I think it should allow for more adoption, but whether it really does or not, I mean, if people could send cryptocurrency and it was going to mean that the exchange rate was going to be better, you know, so it wasn't going to cost them as much money to buy something, say, from Australia that's being sold in, say, I don't know, Germany, because rather than having the horrific exchange rate that the credit card company gives you, you had something much less. I think then it'll have value, but that then relies on PayPal letting you pay using electronic currency too. Somehow. Yeah. All right. Does anyone have any DeFi questions? You know, what if we want to talk about stuff that's hot and all that, you know? No, anyway, good. Thankfully, no DeFi questions. I'm sure I'm the wrong person to ask anyway. Okay, so it's been great that we've had Alexei come along today. And in 2 weeks' time, we're going to have a talk at the same time. So 5 p.m. Brisbane, 10. So we're at GMT plus 10 time zone. And we're going to have Konstantin Klado, who's going to talk about Scale, which is a layer 2 solution. And so that's going to be good. Then 2 weeks after that, at 12:30 p.m. Brisbane, we're going to have Hannah Howard talk about Filecoin. So she's been doing stuff on the Filecoin client and is really knowledgeable about Filecoin. So that's going to be an excellent talk, and that'll be our final talk for the year. Then in late January, Piper's going to come on and talk something about stateless Ethereum, Ethereum 1.x. He's actually going to narrow down that rather broad topic, probably in another sort of few weeks' time. And then 2 weeks after that, I'm going to talk about atomic cross-chain and cross-shard transactions and talk about the methodology that I've come up with and the implementation and how it allows you to have business logic, so functions across blockchains and do atomic stuff. And maybe provide performance numbers and all that. So anyway, hopefully all of you can join for those various talks. And thank you for joining today.
Thank you very much, everybody, for joining. It was a pleasure talking to you.
Yeah.
Thanks, Alexei. Great talk. Thanks, Peter.
Yeah.
Very cool. Thanks.
Thank you.
It was
Thanks,
good.
everyone. Thanks, everyone. Alexei.
Bye-bye.